Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we will discuss the idea of conductance using the bottom up approach that we have been discussing since last few classes, and we will generalize this entire idea, this entire general model of transport, and see how can we use this in the bulk. Basically bulk, how can we deduce bulk transport using the general model of transport that we have been discussing so far. So, just to sort of remind you in the beginning itself that in bulk transport the idea of conductivity is quite important. So, that is why we have started looking at the idea of conductance right from the ballistic and diffusive transport cases. So, let me quickly review what we have been seeing in our discussion. We saw that that in steady state the electronic population looks like this, the current looks like this. The only difference in ballistic and diffusive transport is this quantity essentially. In ballistic transport case, this quantity is the number of modes in the device, and in the diffusive transport case, this becomes the number of modes times the transmission coefficient, where this transmission coefficient accounts for the scattering in the channel, accounts for the scattering because now the channel is long in diffusive transport and electron travels like this on a zigzag path from the source to the drain, and some of the electrons may reach to the drain side and some of them may not reach to the drain side. So, this might be one of the paths, one of the possible paths that the electrons can take. So, this is accounted for by this transmission coefficient Te, and we saw that using Fick's law, by applying Fick's law in this case, in the transport case, we saw that the transmission coefficient turns out to be this. So, Te is essentially lambda E divided by lambda E plus L, where lambda E is the mean free path of an electron with energy E. And in various limits we saw that in various limits, for example, in ballistic, diffusive and quasi ballistic case, we saw what are the values of the transmission coefficient. In ballistic case, it automatically from this expression turns out to be almost equal to 1. In diffusive case, it is very less than 1, and in quasi ballistic case, when the length of the channel is of the order of the mean free path of electrons, it is quite close to 1 but less than 1. Okay. Then we started the idea of conductance, and as all of us know that a very basic relationship between the voltage and the current is this. So, the voltage and currents are related to each other by the resistance of the device, and inverse of the resistance is known as the conductance. So, which means that the conductance is essentially current divided by voltage. So, conductance of an electron at energy E will be the current that is contributed by electrons of that energy divided by the applied voltage. So, in order to sort of derive this expression of conductance, we need to explicitly obtain a relationship between the voltage and the current from this expression, this equation basically. And in this equation, voltage applied across the device, if we apply a voltage, for example, if the source side is grounded and the drain side we have applied a voltage V, that is accounted for by the difference of the Fermi functions F1 minus F2. And what we saw in the near equilibrium case, in near equilibrium case, and when is the near equilibrium case? Near equilibrium case is when we apply a short voltage across the device, the applied voltage is very small, and in that case the difference between F1 and F2 is there, but it is not very large. And in that case we can, by using Taylor series expansion of a function, for example, according to the Taylor series a function can be expanded in this form, we could deduce that the difference between the Fermi functions is essentially F1 minus F2 is equal to, actually it is a matter of convention, in some cases it is assumed that delta EF is, at some references it is assumed that it is minus Q times V, and in that case this difference will be minus del F naught by del EF, delta EF. But using our convention which looks like this, in which case we assume that we have this kind of a device, these are the contacts, on the source side we have EF1 Fermi function F1, on the drain side we have the Fermi level EF2, the Fermi function is F2, and the applied voltage basically brings down the drain side Fermi function and the drain side Fermi level, and this difference between EF1 and EF2 is given as Q times V. So in our case delta EF, which we define to be EF1 minus EF2, is Q times V. In some sources, in some books and papers, delta EF has been defined as EF drain side minus EF source side. In that case this delta EF becomes minus Q times V, and F1 minus F2 becomes, in that case this becomes minus del E by, sorry, minus del F by del EF times delta EF. But in our case this negative sign is not there. Okay. This expression can be written as F1 minus F2 can be written as minus del E, del F by del E. So del F by del EF can be written as minus del F by del E times delta EF, and the reason for that is that the Fermi function has a general form like this. It is 1 divided by 1 plus exponential E minus EF by KT. So it means that if we take a derivative of F with respect to EF, it will be just the negative of derivative of F with respect to E. You can, this can be a small exercise, just try it out, it is a simple derivative technique. So from here what we see is that the Fermi function is a function of energy, it is also a function of Fermi level. Also the Fermi function is a function of temperature as well. So in our treatment, in so far we have assumed that the temperature of source contact and the temperature of the drain contacts are the same. So T1 is equal to T2 is assumed, because if the temperature is different, in that case also there might be a difference in the Fermi function and that might result in a current conduction. Those are known as the thermal effects or thermoelectric devices that we will also discuss once we complete this discussion of general model of transport and then a brief of MOSFET devices. Okay. So, so this is all what we have. Now we are in a position to basically calculate the conductance, because in the current equation, in this equation, we just need to replace F1 minus F2 by this. So, if we do that, I is equal to 2q by h Te times Me times F1 minus F2 dE. Okay. In this equation as well, you can see there are broadly three terms. One is Te, second is Me, and third is F1 minus F2. These three terms actually account for different processes or different physical phenomena that go into the current conduction. Te accounts for the scattering of electrons in the channel, and that is why Te is equal to 1 in case of ballistic transport, because in ballistic transport there is no scattering. Me accounts for the conduction pathways in the channel. How many conduction pathways are available for electrons to travel in the channel? This is a fundamental property or that comes from the fundamental physics of the channel. F1 minus F2 describes the contacts and the applied voltages and applied voltage, and ultimately current is a cumulative, I would say a cumulative effect of all these three things that go on in a device. So, using this expression we can now see that if we put F1 minus F2 to be equal to, from the Taylor series expansion, if we put this to be minus del F by del E delta EF, and delta EF is Q times V, so minus del F by del E Q times V. So, if we do this, if we use these two expressions, this one and this one, what we obtain is I is equal to 2q by h Te times Me times minus del F by del E into Q times V dE. So, what we can see from here is I is 2 q square by h Te Me minus del F by del E dE, this quantity times V, because V can be taken out of the integral because V is not dependent on the electron energy, it is an external parameter that we can control from the battery. So, the ratio or the from this expression from here, what we can see is the conductance, which is essentially the ratio of current and voltage, is 2q square by h Te times Me minus del F by del E into dE, this integral essentially. So, this turns out to be the conductance of the channel, of the device, and this is true for the case, for the ballistic case and as well as for the diffusive transport case. Okay. And please also remember that this is this approximation holds true when we have the near equilibrium conditions, because in that case only this F1 minus F2 can be approximated by the minus del F by del E times delta EF. Okay. So, so this is what we obtain, the conductance, finally this is the expression for the conductance. Okay, now we need to see a few important things here actually. This is finally the expression for the conductance. Now this quantity del F by del E or minus del F by del E is an interesting quantity. Here it is written as del F naught by del E, which is fine. So what F is a Fermi function, so the way it looks like is 1 plus E minus EF by KT. So this is an important part, important mathematical part here, which we always need to keep in mind. This is an important quantity, and let's see how it looks like, because this is going to appear in conductance, this will be there in the current expression, so we need to properly see what it is. So let's start with how the Fermi function essentially looks like. So this is the form of the Fermi function. So if we plot the Fermi function as a function of energy, this will be this will look something like this. So the value of the Fermi function changes right from 1 to 0. So up to a certain energy it is 1, and the energy where it is half, that energy is known as the Fermi level. At low energies it is 0, at high energies the Fermi function is 1. Okay. So now if we try to plot what del F by del E look like, let's see how it may look like. So this is E, this is del F by del E, and if we have EF here, for example, at this point, so del F by del E versus E will just be the gradient function of this function, the function that is plotted here on the right hand side. So the gradient of this function at low energies at these points is 0 almost. So this function will be 0 at low energy values. So this will be the, so at low energies, the energies which are way below than the Fermi level, the del F by del E function is 0. As the energy starts approaching EF level, we start seeing some gradient there. So the gradient at this point roughly is this, and this is the, this angle theta is greater than 90 degrees, so the gradient is negative. So initially the gradient was 0, then gradient starts becoming non-zero, negative. So this is how gradient, at this point the gradient is negative, but with high magnitude. At this point also gradient is negative. So generally this function will be, but as soon as we start going, so up to EF energy level, this magnitude of the gradient starts increasing, it increases essentially. After EF level, as you can see, the gradient at this point is again, the magnitude is again decreasing. So it is again decreasing after EF, and at high energy values, the energy values that are far away from the Fermi level, the gradient again becomes 0. So this function will look something like this, and minus del F by del E function will just be the inverse of this function. We just need to change the sign of this function, we just need to flip this function on with respect to x axis. That will give us minus del F by del E. So, so finally minus del F by del E function turns out to be like this. So, if this is the Fermi level, initially this function is 0. So, it is kind of a window function, and this is a window around the Fermi level, and this function is 0 when the Fermi level is either 1 or 0. When the Fermi level is constant 1 or constant 0, up to those energy values or up to those energy points, this function is 0. So, this is kind of a window function. Okay. In addition to this, if the temperatures are very low, let us say at extremely low temperatures, the Fermi level will be step function, as we all of us know. So, the Fermi level at very low temperatures is a step function. So, this is the way it looks like. So, let me plot both of them close to each other on the same reference. So, when we have a very low temperature, in that case, if we plot F versus E, this is kind of a step function. And in that case, this function becomes like a delta function. So, this holds true when T is close to 0 Kelvin or extremely low temperatures. This is at higher temperatures. So, that is one thing that is there, that this del f minus del f by del E function is a window function. It is 0 for extremely small values of E and it is 0 for extremely large values of Z, but around the Fermi level it is kind of a window function. Second important property of this function is that if we take sort of the derivative of this function, if we take this derivative minus del f by del E over all possible values of energy, let us try to calculate this derivative. So, if we do, this is a simple maths, the derivative minus del f by del E times dE, dE and del E goes away because at the moment we are only considering that the Fermi level is constant, temperature is constant. So, the Fermi function is just the function of energy, and so del f by del E becomes dF by dE and this goes away. So, what we are left with is minus f minus infinity to plus infinity, or f if we change the limits. Now, the Fermi function mathematically is this E minus EF by KT. And if we assume that EF and T are constant for a given system, if the Fermi level and the temperature are constant, then F at E tending to minus infinity will be 1 divided by minus infinity. E to the power minus infinity is 0, so it becomes 1. And the Fermi function at extremely high energy values, E tending to infinity, if we evaluate the Fermi function at extremely high energy values, it is 1 plus exponential infinity. So, it tends to 0. So, this upper limit minus f at minus infinity at extremely small values of energy, f is 1 and 0 at extremely high energy values, which is also clear from the plot. If we have a general plot of Fermi function, it is 1 at very low energy values and it is 0 at extremely high energy values. Okay? We do not even need to do this maths. So, this is essentially 1. So, the integral of minus del f by del E over E is 1. Okay. So, these are two things that we need to keep in mind. One is that minus del f by del E is a window like function, and second is that the area that this function sort of covers with the energy axis is 1. So, which means that the area in this window is 1. This area of this window on the energy axis with respect to energy axis is 1. With these two things with us, now let us come back to the expression of the conductance that we derived. So, the conductance is 2q square divided by h Te Me minus del f by del E dE. This expression can equivalently be written as like this. So, we can write this expression to be like this as well, because the integral that we are writing in the denominator is 1, as we have just calculated. The value of this integral is exactly equal to 1. So, we can always divide by this integral, not a problem at all. Now, if you see this expression, this can be written as sort of the average of over the, this average is taken over minus del f by del E. So, it means where GE is essentially 2q square by h Te times Me, Te times Me. This is known as the conductance function, and if we take the average of conductance function over this window, which is also known as Fermi window, minus del f by del E is also known as Fermi window. If we take the average of this conductance function over Fermi window, that will give us the total conductance of the device, and that is an interesting result. This turns out to be the conductance of the electrons at energy E, and it is known as the conductance function. And conductance function. So, the total conductance can be written as GE minus del f by del E. We are taking average of conductance function over Fermi window okay. It also has an interesting interpretation which we will do in our coming classes as well, that this is also the conductance of one conduction pathway, and that is this quantity, this constant number. This is, that is why known as the quantum of conductance. This is the conductance of one conduction pathway. It is just this quantity 2q square by h, and the total conductance of the device will be in near equilibrium conditions. Please remember that it will be the average of the conductance function over the Fermi window. Okay. Now, in the case of diffusive transport, this conductance function is GE is 2q square by h TE times ME. This term is essentially 2q square by h gamma E pi dE by 2. Let us try to see how the conductance function looks like in the case of ballistic transport and in the case of diffusive transport. So, in the case of ballistic transport, in ballistic case, the conductance function is 2q square by h, gamma is h bar by tau, and tau is L by average velocity in x direction. Pi d is for a 2D channel, since we are considering we are doing all the discussion for a 2D channel, this d is W times L times G 2D E by 2. This h bar can be written as h by 2 pi. So, h go away, 2 and 2, pi with pi. Okay. So, what we are left with is L by L. So, GE is essentially q square average velocity in x direction G2D E by 2. So, this L is, if we keep the L, we need to divide by L, or this can alternatively be written as q square dE divided by 2 times tau E, because tau E is L by Vx. So, this is the conductance function for the case of ballistic transport. This is also true in the case of diffusive transport. Just in case of diffusive transport, the tau E will be, instead of L by Vx, it will be L square divided by 2dN. Okay. So, let us do a small calculation. We could not start the bulk transport case today, but we will do that in the coming class. In diffusive transport case, this will be the same. Tau can now be written as, tau is essentially L square divided by 2dN. So, this conductance function is q square dN dE divided by L square. 2 and 2 will cancel with each other. Okay. And in the case of ballistic transport, this will be the conductance function. Okay. So, just to sort of briefly recall what we discussed that in near equilibrium transport, F1 minus F2 can be written as minus del F by del E times delta EF. From there, we can deduce that the conductance of the system, both in ballistic and diffusive transport case, is the average of the conductance function over a Fermi window function, over the Fermi window, where Fermi window is minus del F by del E. Okay. So, please keep these ideas in mind, these are important ideas. It means that from our plot of Fermi window, that the conduction pathways that are far away from the Fermi level, they do not contribute in the conductance. So, we will discuss more about this in coming classes. Thank you for your attention. See you in the next class.